AP exam questions have the same concepts as your homework, but they're like intense. And you have to kind of know all this. So let's read this. It said a coin rolls at a constant velocity in a circular path inside a cone as shown. The radius of the curvature of the coin's path is r naught. And the surface of the cone is at the angle naught to the horizon. The coin is then moved to another cone whose surface is at an angle sub 1 such that tangent sub 1 is equal to 9 times tangent sub naught, or theta naught. So then the coin travels in a circular radius of the curvature r1 is equal to r naught divided by 4 at a constant velocity of v1. Which of the following correctly relates v1 to v naught? So we have to mathematically show what ratio is shared between these two. Okay. So now this one is a little challenging. This can be done with forces. The forces exerted on the coin are the normal force, which acts perpendicular to the surface of the cone. So let me just let's sketch this out a little bit so I could show you guys what that means. So what they're saying is there is a circle. If I look into this cone, there's a circle. Okay. Now remember, the normal force pushes against an object, right? So if I want to think of it this way, I'm just doing a bird's eye view. I'm looking up from the top into this thing. This is r naught, okay? And we have our coin here, but the normal force pushes this way because the coin is actually pushing out this way. Well, isn't that the centripetal force? Right? So then we've got to think about the normal force, which acts perpendicular to the surface of the cone at the angle theta naught to the vertical. Okay? So let's kind of unpack that. So remember, this is y and this is x. So if I were to figure out the sum of the forces in the x direction, that would be, you could think of that two ways. You could say the mass of the coin times the acceleration in the x direction. Boy, that's not a very good A. I have to use this new software because the other software, I don't know, I just haven't, the computers aren't really set up for the software that we have. I loved Google Jamboard, but Google just discontinued it. And then that is actually equal to the normal force in the x direction. Okay? So there's a centripetal force that goes in this way. Now let's think about the y. So I'll do the stuff in the y direction here. And so that means the sum of the forces in the y direction also is the mass of the coin times the acceleration in the y direction. So remember, like, gravity is pulling down, right? But the coin doesn't fall up or down, right? So if we think about this in the y direction, that should be equal to the normal force in the y direction. And then going in the negative y direction would be the mass minus the acceleration due to gravity. So this coin This coin is traveling around this circular path. Its velocity is good enough to where it kind of keeps it in this path. It wants to go straight, right? It has a tendency to want to go straight, but the cone forces it back in. That's this force. And when you think about a force going in this direction, that is the sum of the x forces. Okay? It's equal to the normal force. And then when we think of the y direction, there's two things. There could be a y component. See how they put this on an angle? So the implication is the cone is angled, therefore the coin is that's gonna have an impact on the coin. So then, according to Newton's second law, which acts downward, the second law of motion can be applied to the vertical and horizontal components of the forces exerted on the coin. So you have an x component and you have a y component. So because the cone is at an angle, it does push. Let me draw it over here. Your normal force for the coin goes this way, but we're going to have an x component of that normal force that goes this way, and then we're also going to have a y component of that normal force. That's why we've labeled these as normal force in the x direction and normal force in the y direction. So we're just labeling things. So then to figure that out, let's deal with this f of x stuff. So then that means if I have the mass times the acceleration in the x direction is equal to the normal force in the x direction, well then that's equal to the mass times the tangential velocity over the radius of the circle, right? And then this should be equal to the normal force, because that's the resultant vector we have, times sine of theta naught. Okay? And just to kind of we're going to do a lot of math here. What we're going to do is we're going to try to find the relationship. We're basically going to have a bunch of stuff we're going to solve for v, right, based on v naught. So technically this would be like your v naught, right? And then we'll do the other thing for v1, and then there'll be like some sort of scalar multiplier when we're done. Does that make sense? All right. So then when we talk about the y direction, because it's not going up or down, then that means that in the y direction, let me write it over here, this whole thing should add up to 0 because the coin isn't going up or down in the y direction. So the sum of these, which is the normal force in the y direction minus mg, equals 0. So then we add mg to both sides, and we get mg is equal to the normal force in the y direction, and then let me move down a little bit. These are more like the free response questions. That's why I'm giving these to you. Well, the y component of this would just simply be mg is equal to the normal force, whatever that is, times sine of, or not sine, cosine of theta. My bad. And I know that might throw you off a little bit. And if you stick with me, I kind of gloss over this. I got to remember I got to explain everything. Theta naught. So back to the picture. Up here, we have, if you think about the radius of the circle, let me change the color so it doesn't confuse you guys. We'll do orange. So I have the cone that's like this. It's on this surface. Right here, I have the angle theta. Then I have a radius here. The coin is here. Well, guess what that angle is? Well, these are like parallel lines, aren't they? And this is the transversal. So if I imagine that this is the transversal that goes this way, this is a congruent angle. So that's the same as angle theta naught and theta naught. So there's a little angle right here that's theta naught. That's why we're able to justify this theta and this theta. And if you do the math on the what is y and what is x versus, based on what is the adjacent, what is the hypotenuse of the right triangle that it forms, turns out in this particular case, our y components, we have to use cosine, and our x components, we have to use sine. Okay. So anyways, we're getting kind of there. So I have a cosine over here, and I have a sine over here. Well, I can combine these two equations, right? Well, how do I do that? Well, I can divide this equation. I can take this whole equation and then divide it by this equation. I'm going to say mg equals the normal force times cosine. Now, this is going to be a little bit of a reminder of your geometry. I don't know if you guys even know this, but sine of theta over cosine of theta equals what? Does anybody know off the top of their head? Yes. Yeah, it's tangent. These will cancel. The masses will cancel. This actually goes on the bottom of this mathematically. So now we've got tangent of theta naught, and I apologize for the handwriting, it's beyond my control, is equal to, and remember this velocity is v naught squared all over r naught times g. Okay? So from there, I want to solve for v naught. So the way that I do that is I'm going to multiply both sides by this, and then the next line I get r naught g times tangent of theta naught is equal to v naught squared, but then I'm going to take the square root of both sides. I've solved for the tangential velocity. So I don't have any numbers, but if I knew the radius, if I knew the number for the radius, and I knew the angle theta, I could calculate the tangential velocity of that coin. Does that make sense? Sort of? Okay. Whew. So we're halfway done. I have a formula that does this. We're going to kind of go through a similar process to get V1. So now substituting the values for the second scenario yields something a little different. All right, so what does that mean? Let me make a little space. Now this type of question on this type of question would be worth about 10 points. I'll show you how they score the AP exam, but it's important that we kind of go through these types of questions now. If I did the same process for V naught, what I would end up with would be, let's go through the same process by just plugging in what they said that we needed to change. So we would have, I'll do this one in green. So we end up with V1 would equal the square root of, instead of R naught, we would have R naught divided by 4, right? Oh, should I go through it? Yeah. Times G. And then now this is a tricky one. And I want to show you where it comes from. See this line right here? Well, let me move some stuff around so you can see the line. It says that tangent of theta is equal, whoops. It says that tangent, whoops. It's telling us that if, because we have to plug in tangent of theta 1 to replace tangent of theta naught. And this should have a theta naught here. That's equal to 9 times tangent of theta. So I'm going to say tangent of theta 1, but really it's the square root of the radius over 4 times g times 9 times tangent of theta naught. Okay, well, we're almost done. So in the next line, over here, I can pull this out. So since all of these are being multiplied, that's the same as saying the square root of 9 over 4 times the square root of radius naught times g times tangent of theta naught, which is the same over here. Well, what is the square root of 9 over 4? What's the square root of 9? 3. What's the square root of 4? 2. And so this is r naught g tangent of theta naught. And then this is, remember, this equals V1. This equals V1. Well, isn't this right here? Isn't this right here V naught? So then I would get V1 is equal to 3 halves V naught. Does that make sense? No? That's okay. So it's a lot of math. Now, all this stuff you guys kind of know, but that's why we do these hard questions. And here's the thing about physics. Once you do this hard question like this, next time you go to do it, it'll be a little easier. So I got to give you these hard problems and go over them and explain. Yeah, they will. It'll be easier. One day you'll go to do the work and you'll be like, oh, I kind of get what I'm doing. But it's a process. Are there any questions about what we've done or how we've done it in this process? Okay. So let's post that one.